I wanted to carefully go through an example that you already encountered on one of the worksheets just to make sure that everybody is completely comfortable with the topic of multiple coins. So imagine that you have 2 fair coins and 4 flips of each coin. Well, we already know from an earlier lecture that the table of all possibilities is this, and that would be true for both coins, right? So we have that for one coin, we have that for the other coin. Now the question is, how do you correctly combine the statistics for the 2 coins? Well, first let's try to answer how many total states are available. And when I'm talking about states here, I mean what I called small-scale states in the worksheet, namely tracking the order of heads and tails. We'll eventually call those microscopic states when we get to physics problems. Okay, so for one coin it's pretty easy, right? If we're just considering the coin on the left, ignore coin number 2, then the number of states available is just the sum of these numbers, right? It's the number of combinations, so 1 plus 4 plus 6 plus 4 plus 1 gives you 16. Now that would be true if you only had one coin. You might say, well wait, the second coin is identical, so we have another 16 possibilities over here. That's true, but now we have to worry about how these 2 coins combine. You don't just add the number of states independently for each coin, you'll get that wrong. The number will be greater than 32, as we'll soon see. So what do we do instead? Well, an easy way to think about this is to say, alright, let's just pick a particular outcome for coin number 1. Let's say that we got 4 heads. Not the most likely outcome, but whatever, that's fine, we'll pick that outcome. What are the possible states for coin 2, given that coin 1 has 4 heads? Well, it's all of these, right? You can have any of these 16 possibilities because coins 1 and 2 are independent of one another. So that tells you just for the first row of coin 1, we have 16 possibilities for coin 2. Let's move down and consider a different outcome over there for coin number 1. Let's move down 1 row to row number 2. Now we have 3 heads in a row followed by 1 tail. How many total states can you have just associated with that outcome for coin 1? Well, again, you have 16 possibilities for coin 2. The coins are independent. So we had 1 times 16 plus another 1 times 16. We're going to go through every single row here on the left, and we'll have to go through 16 rows. So each of those numbers, 1, we're going to multiply by 16. That tells us that the number of total states must be 16 times 16. Another way to think about it in terms of omega, total number of states, is we know that there's 2 to the 4th possible states just for coin 1, independent of coin 2. There's 2 to the 4th for coin 2, independent of coin 1. To find out the total number of states, you actually multiply the number of states for each system independently. So 2 to the 4th, which is 16, times another 2 to the 4th, which is 16, gives us 16 times 16, which is 256. So there are a total of 256 states now when you involve 2 coins and consider all possible combinations for 4 flips of the coin. That's very different from just adding 16 and 16 to get 32, which would have grossly underestimated the number of total states. Alright, that's one question answered. Next question we want to address. How many states do we have with exactly 2 heads for each coin? And this was also asked on the worksheet. Well, now you can go through and use exactly the same logic. You have to restrict yourself to having 2 heads for each coin. So in that case, if we pick a row over there for coin number 1, how many corresponding states could you have for coin 2? Well, it's just this value, right? Because those 6 combinations will give you 2 heads for coin 2 also. None of the others will, though. You can't have 4 heads for coin 2. In that case, we want exactly 2 heads. That would violate that. Obviously, we can't have 0 heads. So you can only have 6 combinations for coin 2 with that state for coin 1. But you can walk through all 6 of those states for coin number 1. You can probably see where this is going. That means after you've stepped through all of those, and I won't go through all 6, then the number of states with 2 heads, and I've abbreviated that omega AB with the result 2H. You could write it a few different ways, that's all I was trying to convey with that. Well, it must be the number of states for coin A with 2 heads times the number of states for coin B with 2 heads. That's going to be 6 times 6, which gives you 36. So there's 36 possible states with 2 heads for each coin. The last question I want to address, which was not covered on the worksheet, is what is the probability of both coins flipping heads exactly twice? Well, we have all the numbers of states, so all we need to do is correctly combine them to get a probability. The probability of getting 2 heads with both coins is omega AB with the result 2H divided by the total number of states omega total. So we already have both of those numbers. It's just going to be 36 divided by 256. That probability is 0.14 or 14%. Now you can see that this is substantially lower than the 37.5% that was the probability of getting 2 heads with only a single coin. But that makes sense, right? Now you have this other variable, the other coin can do whatever, and even if it is most likely that it will come up with 2 heads as compared to any of the other results, it's still the case that it can do other things. And so coordinating both of these coins is tougher. That means you have a reduced probability of both of them coming up with 2 heads.